Hello, ladies and gentlemen. My name is Vyacheslav Kostarev. I'm a student at the Department of Nuclear Power Plants and Renewable Energy Sources at Ural Federal University. The subject of my report is modeling of the combined design of radiation protection and thermal insulation of pipelines with radioactive flows. Some nuclear power plants pipelines with hot radioactive flows requiring application of thermal insulation are situated near the staff moving routes and create additional radiation background which can make the noticeable contribution into the irradiation dose. Concerning this, the design of combined units of thermal insulation with radiation protection attracts possible interest. The prototype of such protection was developed at the Department of Nuclear Power Plants and Renewable Energy Sources, and the patent for the invention was received. The possible design of such combined protection is shown in the picture to the right. In this work, the authors made a complex radiation and thermal and hydraulic simulation of the combined radiation protection and thermal insulation to determine the optimal thickness of the protection and the rates of irradiation doses, which the nuclear power plants personnel can achieve with the application of such protection at the pipelines of rooms with periodic access. The simulation of radiation protection was performed with numerical codes using Monte Carlo method. The material of radiation protection studied is the alloy MT17C, consisting of 19% of tungsten, 6% of nickel, and 4% of copper. The radioactive nuclide considered was cesium-137, with volume concentration of 10 grams per liter, and specific activity of 7.96 thousandths becquerels per gram. To set the isotopic composition, it was assumed that the coolant contains cesium-137 only. The pipeline is made of stainless steel and its diameter is 100 mm. The goal of simulation is the dose rate at different distances from the pipeline, at the pipeline surface, and 1, 10, and 100 cm distance. The simulation of thermal insulation was performed with SolidWorks flow simulation. The insulation was made from mineral wool of 43 mm thickness. The pipeline was surrounded by air. A water flow with pressure of 16 MPa and temperature of 330 Celsius was set in the pipeline, which correspond to the parameters of VVR first circulation circuit. The velocity of the coolant was set to 5 m per second. The calculation goals were the temperatures of the inner and outer surfaces of the protection. To reduce the calculation demanded time, it was decided to exclude the bolts and joints between the protection layers. The model created in SolidWorks can be seen in the picture to the right. Here, the radiation protection simulation results are presented. The rates of irradiation doses were calculated for different protection thickness, from 0 to 14 mm, and also various distances from the pipeline, from 0 to 100 cm. The author decided to take the radiation protection thickness equal to 10 mm for further calculation. This thickness ensures the minimization of irradiation doses for the nuclear power plant staff. Here, the dependency of the irradiation dose attenuation from the protection thickness is shown for the different distances from the pipeline. In this picture, the temperature field in the pipeline with the coolant flow and in the surrounding air is shown. It is obvious that the application of mineral wool of 43 mm thickness as an insulation gives us the temperature of the outer surface, which corresponds to the requirements of the regulations. The upper picture shows the temperature on the surface of the pipeline and inside the radiation protection and thermal insulation. It can be seen that the temperature in each layer also corresponds to the requirements of the regulations. The lower picture shows the dependency of the flow temperature on the distance from the pipeline axis. It can be concluded that the optimal thickness of the radiation protection was determined, which equals to 10 mm. The diagram of the irradiation dose rate reduction with the distance for the protection thickness of 10 mm is given in the picture to the right. The markers show the characteristic distances 0, 1, 10, and 100 cm from the pipeline surface. The irradiation rate calculated on the pipeline surface is 7.291 microsievert per hour, which is lower than permissible 48 microsievert per hour. The plots of temperature distribution on the pipeline surface with the application of thermal insulations are obtained. It is proved that use of such insulation design in combined protection ensures that the temperature does not exceed the maximum permissible temperature of the pipeline surface. It can be concluded that the combined quick removable radiation protection and thermal insulation has significant prospects in reduction of irradiation doses of personnel working in the rooms with pipelines with high temperature radioactive flows. Thank you for your attention.